All right, I think we can go ahead and get started with the webinar. Welcome everyone who has joined us already, and welcome to those who are watching later on the recording as well. For those of you who don't know me, I'm Rodrigo Rose. I'm a volunteer with the Aerospace Technical Group for HFES. I also work full-time as a system safety engineer for Beta Technologies, an eVTOL company, and doing some human factors there as well. We've been running this webinar series that is meant to highlight interesting human factors projects in the aerospace industry. This is the second webinar in our series, and today we have the privilege of having Andrea Sparko and Divya Chandra from the Volpe Center to talk about a project on flight deck perspectives on departure procedures for multiple airport route separation. I'll let them introduce themselves and introduce the presentation. And once they're done presenting, we'll have a little Q&A session. So Andrea and Divya, take it away.
Thanks, Rodrigo. So I'm Andrea Sparko. I'm an engineering psychologist in the Human Factors Division at the Volpe Center. Volpe, for those who don't know, is part of the U.S. Department of Transportation. We're under the Office of the Secretary, and we do research we're a fee-for-service organization with sponsors from across the different transportation modes through the different operating administrations and others. The majority of my work has been in flight deck human factors, but I do a little bit of work in other modes as well. And
Hi,
you'll hear
everybody.
about flight deck stuff soon. So
Okay.
Go ahead, Divya.
Sorry. Hi, everybody. I'm Divya Chandra, also with the DOT Volpe Center. I've been here for over 20 years, so a long time, mostly doing flight deck human factors work for the Federal Aviation Administration. And I did a lot of the work that sort of went into the earlier sort of background that Andrea will cover very briefly for this talk, and hope you enjoy it.
So again, we're going to talk about a study that we completed pretty recently that looked at flight deck perspectives on departure procedures for multiple airport route separation, which is a concept under development by the FAA. I'll point out that this work was funded by the FAA. We received our money from the FAA Human Factors Division, and this work also supports the Office of Aviation Safety. So in order to understand our study, a brief introduction of PBN, performance-based navigation, is useful. So performance-based navigation, or PBN, is an alternative navigation to conventional navigation. Conventional navigation relies on these ground-based navigation aids, and the precision of the navigation decreases as you get further away from those navigation aids. With PBN, which includes RNAV and RNP, the navigation source can rely on space-based waypoints that are satellite-based, and it allows them to have more precise routes. The difference between RNAV and RNP is that RNP has an added capability of self-monitoring, which allows it to have even more precise flight paths, and it also enables these curved paths that you see here on this image. And the PBN was a key component of the FAA's next-gen system. It is often used to design departure, arrival, and approach procedures into and out of airports. And it requires flight crews to have specific training to fly these types of procedures, and it requires the aircraft to be properly equipped. We have done we've done quite a bit of research on PBN in the past, and we have noted that there are some specific challenges associated with PBN. So you could see here an example of a PBN charted procedure. PBN can have additional or more constraints in latitude or speed, for example. It can have complicated instrument procedure designs and thus charts associated with it, sometimes with non-standard layouts. And ultimately, this can result in challenges related to increased reliance on automated systems in the flight deck, more complicated decisions about whether or not to accept or reject a clearance. For example, if you have to make sure whether you can, as a pilot, be able to meet some of those constraints that are charted along your route. And of course, this leads to sometimes operation or difficulties with the operational deployment of these types of procedures. Our current study is motivated by the fact that PBN instrument flight procedures, or IFPs, are being considered for supporting new operational concepts, such as a proposed air traffic control concept called MARS, multiple airport route separation. And of course, as the use of PBN expands, there is a need to understand the evolving impacts of PBN IFPs on operational concepts and flight deck tasks. We talked about how we've had some previous research that looked at complexity associated with PBN on flight deck tasks. There's also been some research on the air traffic side related to MARS, and we have a previous study, Divya and I, that looked at flight crew issues related to PBN arrivals and approaches for MARS operations. The study that we'll talk about today looked at PBN departure procedures with a focus on issues that might be relevant to MARS. The primary goal of MARS is to deconflict terminal area traffic between adjacent airports. So on the left-hand side here, you see an image that depicts on the left an existing conflict between two approach procedures in the New York area. And on the right, you'll see how MARS proposes to deconflict those two procedures by building separation into the instrument flight procedures. So as you can see on the right here, MARS does this deconfliction by building a PBN segment on this approach procedure into JFK. And you can see that it has a parallel segment with the LaGuardia procedure. When those aircraft are on those parallel segments, their separation may be reduced below 3 nautical miles laterally. And their separation, the safety is ensured as long as the pilots stay on their planned charted route. So you can understand why the increased use of PBN routes is a key component of this MARS concept because of that increased precision associated with PBN procedures. One final thing on this slide that I'd like to point out is that, this example, of course, uses two approach procedures as an example. Our study is looking at departure procedures only, but the MARS concept can utilize all different combinations of terminal instrument flight procedures. So that could be two departures, a departure with an approach, or a departure with a missed approach, and so on. Right, we'll go into some project specifics. We conducted this research in 2 phases. We're going to mainly talk about phase 2 today, but as a little bit of background, we did do a phase 1 where we talked to subject matter experts at the FAA and did a literature review to identify human factors knowledge gaps and gaps with operational safety data, and just developed a research plan to address those. For that background research, we had a blend of focus areas. We, of course, started from the flight deck perspective. We were interested in PBN departure procedures. We were also interested in reduced separation operations involving PBN instrument flight procedures. This includes all types of instrument flight procedures, not just departures. MARS is a type of reduced separation operations with using PBN IFPs. And then that little sliver of overlap between the 3 different components is the MARS departure concepts, where we're really focused. We identified 4 research gaps in that background research for phase 1. The first one being that flight crew issues associated with PBN departure procedures have not been systematically gathered and analyzed recently. We mentioned that there has been some past research, including some of Divya's and my own research, but a lot of the research hadn't been updated much in the past 10 years or so. A lot's changed with PBN since then. Related to the first research gap is that additional research is needed to understand what factors contribute to flight path deviations on departure procedures. We also noted that the existing research that was out there on PBN departure concepts doesn't really focus on flight crew issues related to Mars. So we wanted to hone in a little bit more on issues that might be relevant to Mars. And finally, we realized that data are needed to understand flight crew perceptions of traffic during Mars operations. If you picture a Mars situation, you can understand how, as a pilot, you might be seeing other traffic aircraft out there that are both closer than expected and also in locations that you would not normally expect. So we wanted to see what how pilots perceive those. We had 3 main research activities. You can see them here mapped to each of our research gaps. So there's the project title here, and each research gap is one of these green blocks at the bottom. Our first activity was discussions with 4 technical pilots. This was kind of a low effort introductory task or activity where we're trying to understand current flight crew issues and potential issues with Mars associated with PBN departure procedures, just kind of updating our knowledge before we dived into the other activities. We also analyzed 20 records that we curated from NASA's ASRS program. Those helped us to understand current flight crew issues with departure procedures and reasons that they might deviate. And finally, we had discussions with 9 line pilots to understand reasons for deviations and also their perception of traffic during Mars operations. And we also had a kind of side task, which is a pop-up task, which I'll go over in the next slide or 2, where we had looked at some data that we had requested from the MITRE Corporation to understand how altitude constraints on PBN departures have changed over the years. So to recap, the technical pilot discussions, we were trying to understand current flight crew issues with PBN departure procedures with a focus on reasons or factors that might contribute to flight path deviations. And we also wanted to know what they anticipated might be some issues with respect to departure procedures for Mars. We have 3 main takeaways. The first one being that PBN departures have more vertical constraints than they used to. We heard this from the pilots, and we did confirm it. This is where we use that MITRE data to confirm that, yes, they indeed do have more vertical constraints. Vertical constraints are just an additional thing that the pilots have to check, make sure that they will be able to meet those constraints so it can add workload if you have a bunch of additional constraints. The second takeaway is that pilot requirements and techniques have changed. So pilots now routinely use the flight management system to fly departure procedures. And that just means that pilots now require a deeper understanding of their automated systems in order to fly these types of procedures. Now, I just mentioned 2 key takeaways related to things that have changed, but the third bullet is one thing that has not changed. We learned from technical pilots that ATC amendments continue to pose a risk of flight path deviations. We heard that departure procedures, changes to departure procedures on the ground can be particularly risky due to the timing of that. Departure procedures can also have multiple amendments. So you could have an amendment to your a constraint or your runway, for example, or your whole procedure, and each one of these has to be double checked. For the ASRS analysis, again, we were looking at current flight crew issues associated with PBN departure procedures and what factors contribute to deviations on departure procedures. We selected and analyzed a curated set of 20 records. We down selected these from many more records to really illustrate some of the issues that we're seeing in the larger set. These were records that mentioned deviations while flying RNAV departure procedures, and these were also scenarios that could have occurred under a Mars scenario or ones in which Mars might want to be able to figure out and be able to handle. We analyze these by categorizing them based on intentionality, so whether there was an intentional or unintentional deviation, and we also identified triggers that led to those events. I won't go over this in detail, but this slide provides a few examples of some of the types of events that we put in each of the categories. Unintentional deviations, for example, might be something like errors entering information into or data into the automated systems. Intentional deviations were things related to external events like engine failures or wake turbulence. We also had a few examples or a few records in the data set that had both intentional and unintentional deviations. And we also had a few events that had undesired outcomes that were not route deviations. We saw from the data set that we looked at that some common triggers for unintentional deviations include task management and ATC amendments. Departure tasks are highly time sensitive. There's a lot to do on departure. Pilots are managing their airplane configuration, their flight path, automation mode. They're looking for traffic, completing checklists, talking to ATC. And of course, they can be quickly task saturated, and disruptions and distractions and interruptions can really affect them. And they can kind of fall victim sometimes to operational pressures. I kind of mentioned how ATC amendments can cause additional workload. Again, they can have multiple components, all of which must be programmed or reprogrammed and verified. And sometimes the undesired outcomes are things like high workload or extra radio communications, not necessarily route deviations. For the discussions with the 9 line pilots, we wanted to understand how they perceived PBN departure traffic during Mars operations, again, when that traffic might be closer to them than expected and in unexpected locations. And we also wanted to understand a little bit more about the factors that contribute to flight path deviations. We met with each of the 9 pilots for 1 hour each over Microsoft Teams, and we had them do 2 tasks. First, we asked them to assess traffic in 2 hypothetical traffic scenarios shown on simulated static images of a Boeing navigation display. And then the second task was really more of a conversation where we just asked them to discuss scenarios where they might have to deviate from a departure route, either intentionally or unintentionally. I won't go over this slide in detail either. You can read the range of pilot experience here, but I'll just point out that these 9 pilots tended to be on the higher experienced side. So for the task, we showed pilots 2 scenarios on a simulated Boeing 737 nav display with a TCAS overlay. You can see the TCAS traffic over here. We showed them 4 images for each scenarios, one at a time, but the images depicted the on-chip aircraft seen here as it followed along the departure route. So it was kind of like a stop animation version of each scenario. And for each image, we paused and asked the pilots to just talk through the situation that they saw in front of them, tell us what they might do if they were experiencing this in actual operations. This was a relatively low budget and simple method, so you can imagine some of the limitations that might be associated with that. I won't go over this, all of the limitations here, but I will highlight 2. One was that we did not provide pilots with information about Mars. Again, we only had 9 pilots that we were able to talk to. Ideally, and if we had more pilots, we would have loved to provide half the pilots with information about Mars and do some sort of comparison between the 2 groups. The second limitation is that most of these participants were highly familiar with New York, which is where those scenarios were based. I'm only going to show you the results for one scenario today. This is our scenario 1. This image here shows you an overhead view of the scenario. You can see the own ship is departing out of JFK down here, and the traffic aircraft is departing out of LaGuardia here. We did not show this image to pilots. This was just used by us to visualize and plan out the scenario. We did experiment with the climb rates and climb gradients and timing of the departure procedures in order to intentionally place the aircraft both within 3 nautical miles, which is this green box here, and 1,000 feet vertically of each other. So to put them in that reduced area of separation. That put own ship climbing rather quickly and traffic climbing rather slowly. We did learn that that isn't really characteristic of typical operations at LaGuardia, but it is possible. We analyzed the data by categorizing the level of perceived traffic threat based on what pilots said they would do or think if they saw the traffic on their nav display in actual operations. At level 1, they did not perceive any threat. At level 2, they were aware of the traffic and kind of paying attention to it, but not taking any action. At level 3, they were starting to gather information about the traffic. For example, a lot of pilots said that they would start asking ATC about the traffic if they hadn't yet heard from ATC and had received an ATC call out. And by level 4, the pilots were planning to take action. For example, they might consider taking an early turn. This is the first image of our scenario that we'll be showing you today. Here you can see own ship is on the ground. They're about to take off. They'll go up here, turn left, out towards the score waypoint, and so on. Here's a traffic aircraft. You can see that it's about 5 nautical miles away from own ship. It is 2,500 feet above and climbing. And for this image, no participants were seeking information or planning for action. I'm going to go through the next 3 images a little bit faster. I would encourage you to keep your eye on the traffic aircraft, and I'll talk through the results. They're on the right. Here's image number 2. As you can see, the traffic aircraft is now about 2.5 nautical miles from own ship and 500 feet above and climbing, so a lot closer. At this stage, all participants did perceive some threat. They are either aware of it, watching it, and some people were, in fact, seeking information about that traffic. By image 3, you can see that the aircraft has gotten even closer. It's right in that 12 o'clock position. So if this aircraft does not make its turn, that could be a problem. At this point, all participants perceived at least some threat, and some were planning to take action. Majority were actually planning to take action. And here's our last image, image 4. You can see that looks like we have pretty much finished the turn or just cleaning up after that turn. Then the traffic aircraft is a little bit further away, and it looks like it'll probably be behind us shortly. And at this point, the perceived threat level decreased, and no more participants were no longer planning for action. A few other takeaways from what we heard while pilots talked through these traffic scenario tasks or scenarios. We heard about a lot of different factors that pilots would consider for their traffic assessment if they were doing this in the real world. These are things that pilots asked us about or said that they would look for if they were flying this in actual operations. They asked things like, is this my same aircraft on each image? Can I see the traffic out the window? Is air traffic control going to contact me about this? They wanted to know about climb performance and so on. We also heard a few things about hand flying. We heard from several pilots that they would prefer to hand fly the procedure. And the only reason that they might switch the autopilot on would be if they had a high workload and just needed to shed some of that workload. And they were explaining to us that hand flying, even with the flight director, which is, hand flying is allowed with the Mars concept with the flight, as long as the flight director is used. But even with hand flying, it's not necessarily going to look exactly like it would when it's being flown by an autopilot versus a pilot hand flown. We do not know whether that would show up on an air traffic controller's display or not, if there is a difference, whether it would show up. But that is a question. And we also heard some information about how they set up their TCAS. When we asked pilots to describe scenarios in which they might deviate from a departure procedure, we asked them to describe scenarios in which they might unintentionally deviate and when they might intentionally deviate. When we asked this question, we heard a lot of different examples for scenarios that would involve unintentional deviations. Most, if not all of those, however, were related to interactions with the automated systems. Some examples are here. These include errors reprogramming the FMS after an ATC amendment, selecting the wrong navigation mode, or failing to engage the autopilot when they were supposed to. In comparison, we saw quite a few less examples for unintentional deviations, and we heard a lot of repeat examples across the different participants. These intentional deviations were often in response to external factors like weather, traffic, or things like equipment malfunctions that would require some sort of appropriate non-normal procedure that the pilots would have to follow. Okay, so we just have a few more slides. We'll just wrap up with a few insights. The use of automation systems for PBN departure procedures has increased. Again, we're just reiterating what we focused on earlier or mentioned earlier, which is that pilots are going to need increased knowledge of how these systems work. Flight path deviations continue to occur. You saw just now that we saw many causes for unintentional deviations and relatively fewer for intentional deviations. And a lot of those unintentional deviations were somehow involved interactions with the automated system, which connects us to that first point. And pilots are highly sensitive to the timing of tasks and disruptions on departures. When it comes to Mars specifically, constructing the traffic scenarios was very informative. I showed you an example of one of the scenarios that we developed or that we used. These were, I think I may have forgot to mention earlier, but these were scenarios were derived from the notional scenarios that were provided to us from the Mars program, the FAA Mars program office. And some of them are in the Mars concept of operations. So we did use 2 scenarios for this study, but we did look at many more from the ConOps before settling on the 2 that we did. What we learned here was that many of these applications may actually minimize the time in the area of reduced lateral separation. So you can imagine that if it's just mere seconds that these aircraft are both in this area of reduced separation, especially with everything going on in departure, it may be that they may overlook that traffic, may not even notice it, or that the traffic conflict would be resolved before they even really have a chance to act on it. I noted earlier also that we did intentionally manipulate the scenarios so that we can put them both within reduced lateral and vertical separation at the same time. It was actually really hard to do that. And so we learned that is unlikely to happen, that they will both be in both lateral and vertical separation at the same time, but it is possible. The climb rates and gradients that we use to put the aircraft in that situation are realistic, although maybe a little extreme. So it is legally possible for them to do that. So, we really are aiming here to avoid that worst case scenario where there's some sort of deviation, whether in that reduced area separation. And you saw from the traffic assessment results that in the most threatening image, several pilots were seeking more information about the traffic and were preparing to take action. And we'll just note that these were pilots who were very experienced in flying in high traffic areas, particularly in the New York area where these scenarios were based. And less experienced pilots may react differently. Less experienced pilots might maybe they don't have the knowledge to really notice all of these concerns, but then again, they might be their lack of experience might lead them to find the traffic even more threatening. So when it comes to Mars, we have some considerations for both planning and operations. If ATC procedures may need to be designed to deal with disruptions to Mars operations. We saw that deviations do occur. What happens in these situations? There's probably going to need some sort of procedure the air traffic controllers will need to do. Do they shut the whole thing off? Do they just reroute, for example? IFP designs that are difficult to fly in operations could have higher risk of deviations. Again, we want to avoid that worst case scenario, that there's some sort of deviation when they're in that area of reduced separation. So as new procedures are designed for Mars operations, it will be worthwhile to go back and look at those designs of the existing procedures and make sure that we're using designs that are easy to fly. If Mars IFPs are operationally edited by ATC, that could increase the risk of deviations. Air traffic controllers should be prepared for pilots to ask them about traffic. We saw in our study that several pilots said that they would ask ATC about the traffic. And finally, pilots may perceive traffic differently with traffic displays based on ADS-B. We used the TCAS display because it's universally known and understood, but you can imagine that in the future when Mars is implemented, and I should have said this earlier, but Mars would not be implemented probably for several years. So in the future when Mars is actually implemented, there may be additional traffic displays out there, like those that are based on ADS-B that would provide additional information, for example, information about aircraft trajectory, for example. And that may, of course, affect how pilots perceive that traffic. And with that, I want to thank you for listening to our talk today. We would love to answer some questions if you have any. Divya is going to jump in and help me answer questions, and hope to have a great discussion.
Thank you so much, Andrea and Divya. I will ask one question before turning it over to the audience to ask questions. You mentioned just now some of these implications if we were to implement Mars in the next few years for air traffic control and for pilots. What do you think the implications would be for aircraft manufacturers or designers of aircraft systems? What are they going to have to keep in mind as these procedures start changing, or as we're trying to implement new procedures with aircraft that already exist and have been designed for procedures in the past?
Divya, do you want to take this one? Do you have any thoughts?
I'll try. Yeah, sure. We pointed out that one of the issues is in relation to programming these routes and verifying them and any amendments to them. So one of the issues is definitely going to be how you enter that data and how you review that data so that you're on the correct flight path. What we know from our work, and we presented this to many senior pilots and technical pilots, is that not all aircraft navigation systems work the same, and the default assumptions that they use are different. And so it's hard as a procedure designer, as an FAA person, to sort of anticipate how a different flight management system might handle some of these things. And as we know, flight management systems don't get updated very often. And so you end up with a lot of sort of old software and I would just say if you're a new manufacturer of an FMS type of system, please make it as easy to use as possible. Learn all the lessons things that haven't gone well with the FMSs of today that were designed in the 90s or whatever. Because reviewing and modifying those programmed instructions for your flight management system is a huge component of workload and potential for error for these.
Thank you. Bill, I see you have your hand up. Do you want to ask a question?
Thanks. Great talk. Appreciate it. It's a two-part question, if I may. Do you expect that the pilot lexicon includes Mars? I would think the pilot does not know what Mars means, and that's on the other side of the wall, if you will.
That's a good question. That is still a consideration, an open consideration. At this point, we don't know. That's one of our questions is how much education do pilots need about Mars, if anything? It's kind of designed to be seamless because the procedures are already ones that pilots know how to fly. But that's kind of why we're doing this research, right? To understand, for example, are pilots going to be asking more questions about this traffic when they see it out there? Do they need to know something? And if so, what is that? The next question is, what do they need to know?
Yeah. And I'll just add to that, just one quick thing, that Mars is actually an extension of a concept that does exist called EOR, established on RNP. And we won't get into the details of that other than to say that that's also a term that pilots are not familiar with. And it's been a source of a fair amount of discussion as to whether they should be aware of it. And I would say that's one of the reasons we considered sort of having half the groups of pilots know what it is, but not, or the other half not know it is, because we really don't know what the effects of training and what that training might look like. It would be absolutely minimal, to say the least. It's not going to be extensive training, if at all.
Well, that's great. So therefore, my second part question is like with PRM approaches. I always forget. I remember the acronym: Precision Runway Monitoring Approaches, and where there's an AAUP page, right? There's an additional information page, as well as there's usually a short. Well, that one's a little longer training module, but there's a training module for that sort of stuff. I imagine that's sort of part of what you're considering, is that sort of model, perhaps?
I'll just say that there was, okay, let's go back. So we've been working with a group, long name, Pilot Controller Procedure Systems Integration Working Group, the PEPSI, and they were looking at something similar to that, but with RNP, this EOR concept, and debating sort of what kinds of instructions that pilots might get. There have been some changes to the glossary for the AIM just to define some of the terms. But one of the differences with PRM is that there's a separate controller monitoring that, and there's a breakout procedure if you have a blunder, right? That is not going to be the case here at Mars. The Mars will be run by the regular air traffic control staff. There won't be a different air traffic controller coordinating those two procedures. So it's a little different from PRM and doesn't require that training in that blunder breakout maneuver.
Well, thank you. Sure appreciate it.
Okay.
Do we have more questions from the audience? You can feel free to unmute or put the question in the chat. Okay, meanwhile, while you all think of questions, I will ask another question. So based on my understanding of the presentation, all the scenarios that you ran were in New York, right? Do you anticipate that some of the concerns that pilots had and that they identified through answering your questions would be exacerbated in airports that are maybe different, or in areas that have more terrain around it? Or what other considerations you think would come into play for Mars operations in different kinds of airports?
Yeah, I can take a stab at that, Divya, if you want to jump in after. But we actually did do first we selected those scenarios, we both in New York, not intentionally because we wanted to focus on New York, but those were just the best scenarios we had for what we wanted to look at. But we have done a previous study that looked at New York as a case study for arrivals and approaches related to Mars. We could go on about the challenges related to New York, but yeah, I think it is what we are finding is that it's probably going to be some location-specific considerations. You'll have to think about the local weather and how the operations are, run currently at New York, for example. They're not really using a lot of PBN currently. So as they add in more PBN to support this type of operations, there could be a learning curve there, for example. I'm trying to think of any other examples. Divya, do you want to jump in?
Yeah, I'll give a historical perspective. I've been doing this RNAV, RNP, PBN work for probably over 10, 15 years almost. If you look at the history of it, it became more common to use in the western half of the country. So the adoption rates were much higher sort of west of Denver than they were along the East Coast. And for a long time, that sort of disparity has remained. Like you don't see as much PBN in New York, but also not in Chicago. And so it's not necessarily terrain-based, but there's something about the geography and the sort of location specific conditions that sort of make some of these airports more amenable to PBN than others. I would also say that Mars, the CONOPS has a number of different proposed applications, they call them, around the country, and New York is probably not one of the early adopter areas. You're probably going to more likely see it at LA or other places like that with a little bit more use of PBN already. So I think much like the rest of the adoption of PBN, it's going to be phased based on geography. You mentioned terrain, and I'll just say that places that have a lot of terrain, the Salt Lake City types of areas, Denver, they do use PBN, but they have a lot of altitude constraints. And what we found from our older studies was every altitude constraint is something that the pilot has to monitor in real time. They have to program it correctly, verify it correctly, monitor in real time correctly, because sometimes what the aircraft says it's going to do doesn't happen. At the very last second, the airplane sort of changes its mind and says, no, I actually can't make that altitude constraint. And one of the challenges also is maintaining when you have multiple types of constraints. So if you have a speed and an altitude constraint, you're descending and slowing down. Those are very complicated sort of decisions for the aircraft systems. And so that's why the pilot is in there monitoring all of this. So there are different challenges with flying a PBN IFP from a pilot's perspective, depending on where you are. And that just means when you break out, that's going to have other implications, right? So if you have one airplane in a terrain area kind of break out and say, I need to do something else, then air traffic control is going to have to figure out what to do with the rest of the airplanes around there.
So I know that the ASRS reports are usually kind of de-identified and scrubbed for what airport this actually happened in, or even what kind of aircraft was involved. Did you identify any like trends or correlations between any of these sort of side factors in there that are not just the ASRS narrative or report, but the type of aircraft or the type of operation that it was having and the issues that they observed with the profiles?
I'll speak to that since I probably spent more time with the ASRS data than Andrea did, but a couple of observations. So the ASRS data are in fact de-identified, and what was a little bit surprising to us was in fact the location was de-identified for a number of the reports that we were looking at. So it was I don't know what to make of that, why they were de-identified, but it was a little bit interesting that the specific events we were looking at seemed to have a fairly large percentage. I was trying to look up the number, but it was a significant number of them that were de-identified. I also would say that PBN and the kinds of procedures we're looking for, the RNAV departures, are more common at major airports. airports, right? Especially, you're going to find Atlanta and Dallas and, Washington, D.C. These are the places where this is most commonly used. So it wouldn't be surprising if that's where these events were sort of occurring and were de-identified. So I would just say that RNAV departure procedures are becoming very common. And Andrea mentioned that there are a lot more altitude constraints on them. So I can't say that we know where they are, except for where they are. Like, if you're going to see a lot of them at big airports, that's where these things are going to be.
Okay, do we have more questions from the audience?
I'll just add a comment. Something that is already in the talk, but I just wanted to sort of emphasize that Mars is an air traffic control initiative. And the fact that we're looking at the flight deck perspective is sort of an added thing that we've been doing. So you're going to find sort of more work in relation to the air traffic control perspective on it. And I think it's been a good kind of collaboration we've had with some of the people doing the air traffic control work to say, how's this going to look from the other side? Because I think it's a little bit easy to sort of focus on your own customer and you're designing for air traffic control and you do all the ATC studies, but you have impacts in the flight deck. And we know from EOR and from other PBN initiatives that sort of doing the test on it from one perspective doesn't necessarily mean it sort of works well for the other perspective. So I think this is a really good example of a project where there has been some initiative to look at it from both perspectives, flight deck and air traffic.
Are there initiatives to look at it on a larger scale in terms of getting airlines involved in studying this, or OEMs as well? Are there those kinds of initiatives going on or planned for the future?
All right, I'll just keep going, Andrea, unless you want to unmute. As far as we understand it, there are no other big research initiatives around it in terms of FAA-funded research. I will say that if you have a program like this implemented, or I should say in a sort of trial evaluation kind of system, that's when you'll get more operational data. And usually that data would be internal to airlines and not necessarily shared with public sources like the ASRS database. It's an interesting challenge to work with ASRS because it really is very limited. But when you get to some of the airline data, we don't have access to that, I would say, but we sometimes hear airlines talk about their data analysis. That's also very challenging because even with more data, you don't ever have enough data, right? You don't always know what the pilot was looking at or what the pilot was thinking, and they've forgotten by the time they report it to their airline. But the airlines do internal analyses, and sometimes they share them with these working groups on a holistic basis, and obviously de-identified still. But that's where we learn about some of these problems, and they're really the people that see this stuff early, so by the time it gets to the ASRS database, it's at least months old. And very much the airlines are the ones looking at that data, and they'll look at it down to the runway. They'll say, this airport, this runway, this type of flight condition, this is where we had a number of problems, and we're going to put out a bulletin on that specific scenario. But again, that's not de-identified data, and it's not available to sort of researchers like us.
Yeah, and the FAA
Okay.
isn't just, I mean, they are, I think, talking to at least technical pilots, like management level pilots, when they are developing and reviewing these concepts, right? But yeah, we're particularly interested in the average line pilot perspective, which, as Divya said, you don't necessarily get until you implement it and see what happens.
Yeah, that's really interesting. It's always interesting to see the challenges that you face with the data that's available, and getting access to that data and making sure that it's of the quality and the standard that we need to actually draw insightful conclusions from it. I'll ask one last question, and then I'll give the audience one last chance to ask questions if they have any. For members of our ASTG who have just watched this presentation and are thinking, this is really interesting, really exciting work, and I want to get involved in this kind of research, what do you recommend as a good place to start?
Well, I would definitely recommend Divya's previous work on this. We have a lot of previous papers on this. We have papers on this. We presented this at DASC, Digital Avionics Systems Conference. We have a paper and we have a full, longer technical report if anyone is interested in this. Divya's been doing this much longer than me. And I still feel like it's a very complicated subject matter, and it's very, very technical, and it's hard to get up to speed on it. There's a lot to learn. So good luck. But it's interesting and it's fun.
We should have added, but you can see there the link to the volpe.dot.gov website. If you go on there and search the publications database, which is right up at the top screen, by either the author's names or some keywords here, you will find all of our publications are available to the public, freely accessible there. So you can certainly look at them. Some of them are long, some of them are complicated. I would say more generally, if you are, say, a young researcher and you're just interested in this area of operational issues, I would suggest you learn as much as possible about flying an airplane. I think that's a really important sort of skill subset to have, and talking to people who work in the real world. So whether they're pilots or FAA people, NBAA people, there's a lot of resources out there for you to build up a general area of expertise. And I would say, as a many years ago student researcher for human factors in aviation, it's kind of overwhelming to know where to get a foothold and where to start. But I think that just finding somebody who's willing to sort of sit down with you and answer some questions, and just keep going with the questions. I mean, I certainly did that with my graduate work. I would find, a pilot through a faculty member or place, and this just sort of see how willing they are to share information. Many of them are very interested in sharing information. If you show some interest and a little bit of knowledge, they will help you along.
Thank you so much. That was a great response. I'll give the rest of the audience one last chance to ask any questions. Going once. Going twice. All right. I think in that case, we will end it here. Unless Andrea and Divya, you have anything else you'd like to share? Any closing remarks?
Thanks for the opportunity. I'll also just point out we do have our sponsors listed from the folks in the FAA. We should also give them a lot of credit because they're the ones who sort of promote the idea of doing this research. That's Kathy Abbott and Jeff Kerr. Our program manager, Victor Quach, helps make sure we get the funding that we need to do the work. So I want to thank all the folks at the FAA that were involved and the many, many pilots we talked to throughout the course of all this research.
Awesome. Thank you so much.
Yeah.
And
Thanks
Thank you so much for your time.
Bye-bye.
Bye.